How to blur the background?
For that, you need to go to this video setting, and you can see in choose virtual background, something that will give you the blur thing. There will be option there.
Okay, just
yeah, it is blurred now. Do we have like block the chat for this meeting also? I think for this meeting is allowed, huh? For webinars it is blocked. Yeah, because in its instruction it's not written like we should block here also.
Yes.
Or also holding, once the chair and all this will join, then only we can share the holding slides.
Okay.
Somebody joined and left. That's why I was thinking to have a holding slide.
What? Somebody
joined and left.
Oh.
That's what it was coming to my mind. Should I share the screen also? But once I shared the screen, and then it will be difficult. Okay, let's try to share this.
The screen share will be only till the chat. Once they start speaking, the screen share can be like, we don't have to put this slide, right?
There is some issue with my sharing.
We have to put the holding slide only till before the session starts. Once it starts, then we can remove it, right?
Yeah. Is the screen shared now? Yeah. Can you see?
Yes.
I think this is better to have a folding slide all the way.
Okay.
Because people are coming and like you can have different views to see all the people.
But yeah, like if you have to do like if you keep it on for the whole meeting, then
No, for the whole meeting I will not keep it on. Obviously, other people need to share just before this things started, because it was mentioned that once we greet the session chairs and then only we should start having the holding shares. But people are coming and in between we are only people to see them. Somebody came and then left. I felt that it will be better there so that they will know.
okay.
So
We have to put it in like some speaker mode or something.
Yeah, initially the view, where it is. Oh, I think once the part somebody will join attendee, then only I think it is there. Yeah, again somebody came and left.
There's a black patch right now.
Yeah, because I changed some setting.
Okay. There's a black patch. I can see a black patch.
Still you can see the black patch?
Yeah, in the top and somewhere in the top right also.
Okay. Is it still there?
I mean, there's a small, there's a bit of it, yeah. I think
It got reduced better. Maybe because
but it's hiding that IIT Bombay logo, the top right.
Okay, yeah, because it's exactly there.
I think you can keep it in full screen mode, right? Because is there some full screen mode in the PDF app? I think that.
Yeah, this is my full screen mode, but still.
Okay.
Still, you can see the black patch there. Maybe because of screen sharing. If you stop screen sharing, it will go down. Let me stop it. Hold. What about now, others? Are you again able to see the black patch now?
Yeah, it's there, but it's a bit on the top, but it is there, but it's not hiding anything that significantly.
Go to the Control Shift Alt H, more options. Go to the more options, hiding this control bar.
Yeah, maybe Control Alt Shift and H. If you press it, will hide. I think.
Yeah.
How is this now? I have hidden floating.
Yes, that floating control. Yes, sir, that is correct. That is correct. Okay.
But
Karim, you have shared your screen, right?
Yeah, I right now I've like kind of paused it.
Okay. There's a black screen is going on just. So
Okay.
once you share, then you can see the black patches, right?
Yeah, let's see.
okay, so like.
Hello, Karim and Adarsh. Is everything okay here?
Yeah, we're just trying this sharing thing, and some bad patches are coming. So
Yeah, it's because you may be having a pop-up, some kind of a pop-up on your screen.
Yeah, it is of the same from the Zoom itself, like screen sharing thing, and
Yeah. So the person who's sharing the screen should not click any button. So one person should be sharing the screen, the other person should be managing. So the person who's sharing the screen should not click on chat, Q&A, nothing.
Yeah.
So should I share the screen?
So yeah, can you please share the screen so that I can do
whoever is going to manage the show should not share. So one would be a passive, and the active manager should not share. It's a passive manager, passive host who should share. So whoever is planning to click on the Q&A and chat should just do that, and the other person can do the sharing. Is that clear?
Yeah, thank you. So I will stop sharing now, and others, can you please share if you are ready?
Excellent.
Now it's on.
Yeah, it's perfect.
Okay.
Adarsh and Karim, just a small suggestion. When this session ends at 12:30, before you close the session, you could just make a small announcement that the next agenda on the program is at 2 o'clock and it's a plenary, and maybe you can just say what the title is. Because, something to that effect. We'll meet again at 2 p.m. for the plenary or something. Okay, thanks.
Any other issue that you're facing?
notes that our chair has not joined yet. And it's 15 minutes left.
Okay.
So I need to call him, I guess.
Yes, please. And you can mute yourself before that.
Yeah.
Karim, were you able to connect to the chair?
Any word, Adarsh? Are they reachable?
Yes, sir. I was able to reach them. They're just joining in 2
Okay,
minutes.
thanks. Okay, thanks.
Professor Salabh Bhatnagar has joined in. Welcome, sir.
Yeah, hello.
Good morning, sir. Professor Salabh.
Yeah, good morning. Yes, yes.
Hey, good morning,
Yes,
Professor Bhatnagar.
Yeah, good morning, Dr. Bhatt. Yeah. So I think today Professor Gugan Thope will be taking the lecture, and tomorrow and day after I will come in.
Okay, fine.
Yeah.
Welcome, Professor Lopez. Good morning, sir. Welcome. You are muted, sir. Yeah, welcome, Professor Govind. Good morning.
Can you hear me now?
Yes, sir, we can hear you.
Yeah, I think there was some issue with my sound settings. I think it's now much better. Shall I share my screen and keep?
Yeah, others, could you
Yes, sir.
please
Yeah, I'll just.
Can you repeat? What did you say?
I was just asking others to stop sharing the screen. Now you can see us.
Okay. Is my screen visible?
Yeah, it's showing is started now. It's visible now.
Okay, so let's see if I can write something here. Okay. Let's see if okay. So can one of you tell me who will be accompanying me through this session? Like who will be the session manager?
So I will be, I'm Kareem Shahbaz. I will be accompanying, and me and others will be here.
Okay.
So
Yes, sir.
we can both control.
Okay, so just one couple of points. So see, our session will actually be 90 minutes. Okay, I will announce this at the beginning, and from tomorrow it will be 1 hour long. Okay, and from tomorrow I think the session will be conducted by Professor Shalabh Bhatnagar. Is that okay? So just today's session will be 90 minutes long. So we will inform this to the audience. So let me know when I can begin and okay.
Timing is
Just a little suggestion. This is Ramkrishna. So if it's a 90-minute session, it will be nice if you can just give a some 5-minute leg stretching break at the end of 45 minutes.
Sure, that should be fine as well. Okay.
Yeah. And okay, so the chat here is open. People can speak up. So the idea is to make the tutorials a little more interactive than a plenary session. So please, you may want to see if people can stop you and ask questions in the middle, or so.
Yeah, that is fine. If the question is not very detailed, I'd be happy to take it then and there. If not, we can have a short answer and then discuss it in detail later on. Okay. The only issue is I unable to see the video because on my screen I can only see my notes. Okay, and I don't know if I can see the chat window as well. So I hope the session manager can help me with that. Okay, so whenever you think there is an interesting question, you can
maybe every 15 minutes you can just take a 30-second pause to and then the session managers can
yeah, so I will have pauses in between whenever a particular topic ends. So I will have pauses in between, so maybe some questions can be posed then, and otherwise as well, if there is a bunch of questions regarding some point that I'm covering, it would be good to stop me then and there itself. It's easier for me to explain it then and there rather than waiting for some time and then going back. Okay?
Yeah, and for the participants, they can either type in their questions or they can just raise their hand, and maybe
yeah, anything is fine, just that I am not able to see the chat window or the video. Also, for some time my video will be on, thereafter I'll be writing on my screen, so my video also I'll be switching it off. Okay. So at the end maybe I'll switch on my video as well if it's easier later on, but at this during the talk I'll switch off my video. I hope that is fine.
Okay. So yeah, over to you. You can get started.
Okay.
So you can start next time.
Okay, so hello everyone. My name is Gugan Thope, and today I'll be giving a very loose introduction to stochastic approximation. So this is part of a tutorial on stochastic approximation and reinforcement learning. So today's session will be dedicated to stochastic approximation, and the session that will be done tomorrow and the day after, that will be dedicated on reinforcement learning. So today's session will be conducted by me, and the session tomorrow as well as the session on Wednesday, okay, that will be conducted by my colleague, Professor Shalabh Bhatnagar. Okay, so one more thing regarding today's the duration of today's session. So today's session will be 90 minutes long. Professor Ramakrishna requested that we have a 10-minute break after 45 minutes. So we will try and have a break in between. And fortunately, the session tomorrow and the session on Wednesday, they will only be an hour long. Okay, I apologize for the inconvenience. But I think Professor Bhatnagar and I felt that, this way both of us would be able to cover things, efficiently. Okay, so I'll be switching off my, video. Okay, and I'll be focusing on my slides. Okay, unfortunately, I won't be able to see either your video or your chat messages. But I think there are a lot of support staff over here. Thanks to them, I request that whenever there are some questions that are there, okay, they can stop me and ask me questions then and there. If the questions are, short, I mean, if the answers are short, I'd be happy to, provide them immediately. And if not, okay, maybe we can wait until the end. Okay, so can I proceed with the presentation? Please let me know.
Yes, sir, you can. Time, yeah.
Just a quick check. I hope my slides are visible.
Yes, it's still visible.
Can one of you please confirm if my slides are visible?
Okay, yes, sir, it's visible.
All right. Okay. Yeah, thank you. Okay, so as I mentioned, the topic today is stochastic approximation, and my name is Gugan Thope. I'm an assistant professor in the Indian Institute of Science. So in case there are questions that you have after the talk as well, okay, you can contact me by looking up my email ID and writing to me. All right. Okay, so as a warm up to what stochastic approximation is all about, let us look at the following question. Okay, so the setup is as follows. There is some random variable z. Okay, and we have access to independent and identically distributed samples of this random variable z. So let us denote these samples by z1, z2, z3, and so on. Okay, so this is a very simple setup. There is a random variable z, and we have been given access to samples of this random variable. And let's say the goal is somehow to estimate the expected value of this random variable. And for convenience, let us denote this by the variable mu. Okay, so mu here denotes the expected value of this random variable z. Right. So if someone posts this question to you, okay, perhaps as a naive strategy, you may suggest using some algorithm of the following kind. Right. So the algorithm looks as follows. So let's say at time n, we have access to the values of z1, z2, all the way up till zn, and we would like to come up with an estimate for mu. Okay, so here is a naive approach to estimate this quantity mu. So this is just the sample mu. Right. So far so good. So let us try and understand what are the issues with this approach. Okay, so the issues with this approach is that in order to compute xn, okay, the first issue is that we need to have access to all the samples. Right. So observe that we need z1, z2, z3, all the way up till zn. Right. So only if we have stored these values can we compute the value of xn. Okay, and the other issue is that the computation needs to be redone from scratch each time a new data sample becomes available. Right. So let's say you are at time n, right, and you have access to z1 to zn, and let's say at time n plus 1 you have access to z1 to zn plus 1. So if you decided to make use of this approach, right? Your approach, I mean, your way to calculate xn plus 1 would be, okay, I, get hold of this z1 to zn plus 1, add all of them up and divide it by n plus 1 and obtain an estimate of xn plus 1. Okay, so I'm sure most of you must be wondering in your, in your mind, okay, what is this? Of course, there is an easy way to go about dealing with this. Okay, so what is the alternative? Okay, so the alternative to deal with these issues. Okay, so the first thing we observe is that since xn plus 1 is z1, okay, all the way up till zn plus 1 over n plus 1, okay, we can split it up into two parts. Okay, so in the first part, we add the first n quantities and divide it by n plus 1. And the last or the second part is basically zn plus 1 divided by n plus 1. Right now, since xn satisfies this relation over here, it is not difficult to see that this sum over here can be written as n times xn over n plus 1 plus whatever is there over here, we rewrite it as it is, right? So this xn plus 1 satisfies this recursive relation. So I say recursive because, okay, I have come up with a formula that relates xn plus 1 to the previous estimate, that is xn. Right, and I hope you agree that by massaging this update rule, okay, okay, by massaging this update rule, one can rewrite it as xn plus 1 is xn plus 1 over n plus 1 zn plus 1 minus xn. Okay, so I've just rewritten this update rule in the following way. Right now, let me pause here for a second or two. If there are any quick questions, this may be a good point to ask. Are there any quick questions?
In the setup, where are you assuming it is only IID? Can it be possible to extend to another kind of random variables?
So we will discuss this, through this discussion. Okay, so this is just to give an intuition of what we are trying to do, and we will slowly complicate this setup. Is that okay? So for the time being, we will stick with this IID case. Okay.
Okay, sir.
Okay, but I mean, maybe I can give you a quick answer. Okay, so if you are aware of the strong law of large numbers, okay, we know that this sort of converges to mu, right? So by the strong law of large number, this sort of converges to mu, right? So wherever, I mean, under whatever conditions the strong law of large numbers works, okay, you can sort of make use of this algorithm to estimate mu. So that's like a short answer. Right, so I hope you are aware that the strong law of large numbers doesn't need the IID assumption. Okay, the basic form of strong law of large numbers is stated assuming the random variables are IID. However, if you sort of scan through the literature, you will see that more generic forms of the strong law of large numbers also exist when there is some weak dependence between these random variables as well. Okay, all right. Okay, so the idea here is that, okay, we came up with this update rule, right? So we came up with this update rule. So let's say this is the final algorithm that we came up with. So I say this is an algorithm, right? Because we can iteratively execute this update rule. And, if we start with some x0, okay, we can compute x1, x2, and so on, okay, just by using this update rule. Okay, so what is nice about this update rule is that at time n, okay, at time n, okay, we only need to know the value of zn plus 1. Notice that in this update, okay, we don't need to keep in memory the values of z1 to zn, right? It suffices if we have access to only zn plus 1, right? And the other thing is that we don't have to do update the value of these estimates from scratch, right? So observe that we are doing this updation by making use of the previous estimate. In other words, xn plus 1 is making use of what the value of xn was. Right, so xn plus 1 is expressed in terms of xn. So in other words, we are reusing the computations that were already done. Okay, so in this sense, just by massaging this approach, that the naive approach that we had, okay, we can see that we have managed to come up with a better way to implement the same algorithm. Right now, this is how you will execute this algorithm. Right, so this is how you will execute this algorithm. However, for the purpose of analysis, okay, so whenever I write analysis, the it sort of refers to, like, where would such an algorithm converge to, right? What would be its convergence rates, right? Convergence rates. okay, and so on, right? So basically we want to understand the behavior of this algorithm, okay? So whatever kind of questions that you have concerning the behavior of this algorithm, okay, when we try to answer that question, okay, we will say that we are trying to analyze this algorithm, okay? So for the purpose of analysis, okay, it is useful to rewrite this algorithm as given in this box. Okay, so I'm doing nothing sophisticated. I'm just massaging this algorithm and writing it in this form. Okay, so what have I done? So observe that in this round bracket, I have Zn plus 1 minus Xn. So what I do is I take, instead of Zn plus 1, I write mu, right? Since I have added this mu, I need to subtract it. Okay, and this is what I do. Okay, so I hope you agree that because I'm adding and subtracting this mu, okay, these things cancel off, and what I have over here is exactly the same expression that I have over here, right? So I can massage this algorithm over here and rewrite it in this form, right? And I use some special notations. Okay, so h of xn is basically the first part, right? So in other words, I define this function h so that its value at x is mu minus x, and this mn plus 1, okay, is the second part over here, which is Zn plus 1 minus mu, right? And earlier I had 1 over n plus 1. I will, instead of writing it as 1 over n plus 1, I will use this notation alpha n, which will stand for 1 over n plus 1. Okay, so there is a short typo over here. So this is alpha n. Right, so far nothing sophisticated has happened. Okay, I have this algorithm to evaluate the mean of a random variable. I have just massaged it, and I'm saying that I can rewrite it in this form, where h has this form, alpha n is basically 1 over n, and I will refer to this as the step size. Okay, and this is mn plus 1, which is Zn plus 1 minus mu. Right, so let us make some quick observations about what I have over here. Okay, the first thing we observe is that h is a deterministic function, right? So h of x is mu minus x. Notice that mu, or recall that mu is the expected value of this random variable z, right? So because it's the expected value, this is some deterministic number, and consequently h is a deterministic function. Right, so while this mu, since this mu is unknown, okay, h is an unknown function. So while this h is an unknown function, the form of h is known. Okay, so let me reiterate what I said. Okay, the function h over here is deterministic, right? However, since we don't know mu, h is an unknown function. By unknown, I mean that if I give you a value of x, you won't be able to tell me the value of h of x. Right, the reason being we don't know mu. However, observe that the form of h is known, right? Furthermore, with regards to this mn plus 1, right, if you define fn, the calligraphic fn, to denote the information until time n. Okay, so for those of you who may have done a course on measure theory and so on, okay, you can interpret this calligraphic fn to denote the sigma field, okay, that is defined using these random variables. Okay, so x0 is basically the initial point of this algorithm, right? And m1, m2, all the way up till mn, where these mi's are defined using this relationship over here. Okay, so this basically keeps track of all the information that is available until time n. Right, so if you sort of look at the conditional expectation of this quantity over here, the expected value of mn plus 1 given fn, right? So mn plus 1 is Zn plus 1 minus mu. So I have just substituted that over here, conditioned on fn, right? So fn is basically the connection of it consists of information based on x0, m1, all the way up till mn, right? And m1 itself is a function of z1, m2 is a function of z2, and similarly mn is a function of zn. Right, so you can sort of interpret that when we are taking this expectation of Zn plus 1 minus mu conditioned on this information, we are sort of in some implicit way revealing to you the values of z1 to zn. Right, however, since we have assumed that these z1, z2, z3 and so on, these are IID copies. Okay, the expectation of this conditioned on fn okay, this will not depend on this Fn. So I can remove this conditioning and I can write it simply as expected value of Zn plus 1 minus mu. And by linearity of expectation, this will equal expected value of Zn minus expected value of mu. Now mu is a constant. Okay, so this is precisely expected value of Zn plus 1 minus mu. However, Zn plus 1 has the same distribution as Z, and consequently its expected value will be mu, and consequently this has to be 0, right? So these are the different properties of the different terms that are present over here. A quick summary: this function h is given by mu minus x. This is a deterministic but unknown function. While this is unknown, the form of h is known to us, right? And if Fn denotes the information that is available until time n, then if you take the conditional expectation of mn plus 1 with respect to this information, then one can see that this conditional expectation will be 0, right? So if you ask me, why did I add and subtract this mu? Well, the quick answer to that is that I wanted to ensure that whatever I subtract from mu, it ensures that this new quantity over here satisfies this condition. So you may ask, why do I want to satisfy this condition? Well, you will soon see what are the advantages of ensuring that such a property holds, right? And finally, with regards to this alpha n sequence that we have over here, right? Because we have assumed alpha n to be 1 over n plus 1, right? From your undergraduate course, or maybe even from high school, okay, you can you would be aware that if you add 1 over n plus 1, okay, from n equals 0 to infinity, this will be plus infinity, and if you sort of take the squares of this and add them up, this will be less than infinity, right? So these are the different properties that that one can say with regards to this update rule that we have over here, right? So now one can ask, what is stochastic approximation? Well, a short answer is that any iterative algorithm that has the form that is given in equation 1. Basically, any iterative algorithm which has the form that is given in equation 1, which I'm just rewriting over here, okay, where your step size alpha and this function h and the sequence mn plus 1 satisfy some of the properties that we saw above, okay. So such an iterative algorithm is what is a stochastic approximation algorithm. Okay, so let me pause here for a second or two. Let me know if you have any questions. I'd be happy to take them. Are there any questions? So I'm unable to see the chat. So if there are any questions, please.
So there are
no questions.
Any question in the chat.
All right. Okay. So I hope the idea is clear, right? So even if you haven't, understood each and everything that I mentioned, okay, it is important to know that when I say stochastic approximation, I mean any iterative algorithm that has the form that is given in this red colored box that I drew now, right? And this is referred to as the step size sequence, right? This is the step size sequence. This h over here is what is referred to as the driving function, and this mn plus 1 is what what can be viewed as the noise sequence. Is that okay? So one can ask, or I can ask you this question, okay, have you seen such algorithms before? Well, the answer is that indeed you must have seen some such algorithms before. In particular, you must have seen something called as the stochastic gradient descent. Okay, in the context of stochastic gradient descent, okay, this function h of x is usually the gradient of the negative of the gradient of some function f, right? So so what does stochastic gradient descent mean, right? Stochastic gradient descent, so let's first recall what is the gradient descent algorithm. So let's say I want to find the minima of this function f, then the gradient descent algorithm is basically xn plus 1 is xn plus alpha n, right, minus grad of f of xn, right? So this is the gradient descent algorithm. However, there may be some situations where one cannot access the gradient of a function directly. However, it may be possible to obtain some noisy estimate of the gradient, right? So in that situation, right, instead of running or instead of being able to run this algorithm, we may instead be able to run the following algorithm, right? So this is minus grad f of xn, right, plus some noise mn plus 1. Okay, so the quantity over here can be
Sorry to
interpreted.
interrupt.
Yeah.
There's one question came since mn plus 1 is used again. The question is why mn plus 1 is considered as noise?
Why? Yeah, I'll try and answer that. So this is the noise in the estimate. Okay, so now let me try and answer the question, right? So why this mn plus 1 is considered as noise, right? So let's try to answer this question step by step. Okay, so let's first look at the case where there was no mn plus 1 in this algorithm, right? So algorithm would have been xn plus 1 equals xn plus alpha n, and h of xn is just mu minus xn, right? So this would have been your algorithm. Now notice that in this algorithm, if you start from x0, right, and let's say you run this algorithm. So of course, when I say you run this algorithm, okay, in order to be able to run this algorithm, you need to know the value of mu. Okay, so of course you don't know the value of mu. However, let's for the time being hypothetically assume that you knew the value of mu. So if you knew the value of mu, of course you could execute this algorithm, and if you start from x0, okay, you would obtain some unique value of x1, right, using this update rule. Then thereafter you can use the value of x1 to compute x2, thereafter you can use the value of x2 compute x3, and so on. Right now, this algorithm is deterministic because each time you start from x0, the sequence of subsequent estimates that you will obtain, that is the value of x1, x2, x3 that you will obtain, each time you run this algorithm, you will get the same values, right? There will be no difference. However, as soon as you add this mn plus 1, now notice that this mn plus 1, okay, is defined as follows, that it is zn plus 1 minus mu. In particular, note that this zn plus 1 is a random variable, right? So each time you run this algorithm, okay, the way to interpret is that you are trying to obtain a new or a fresh sample of zn plus 1. Right, you don't execute the algorithm with the same sample z1, z2, z3. Instead, you sort of obtain this afresh, right? So that's what it means to say that you are executing this algorithm afresh. So if you do a fresh implementation of this algorithm, which means you sort of get these estimates afresh and run this algorithm. Now, because these zn plus 1s are random, okay, the value of mn plus 1 would be random. Right, because this value of mn plus 1 is random, I hope you agree that each time you execute this algorithm, right, the value of x0, x1, and x2 and so on that you will obtain will be different in each run. Okay, so in other words, this is stochastic in nature, and that's why or in particular this is the only thing that is stochastic in this update rule. Okay, so that is the first thing to keep in mind. And the other thing is, you asked me why should I call this as noise, right? So why should I call this as noise? Well, the answer to this is, see, if I knew h of x, right, I could have run this algorithm, right, without making use of this, and I would have run this algorithm, and with some effort you will be able to show that whatever x0 you choose, this algorithm will indeed converge to mu. Right, so of course this is like a very vacuous statement, because if you know mu, then trying to use an algorithm to estimate mu is like a vacuous thing. But we will sort of not bother about these statements for the time being. But the point is that if you knew mu, you could execute this algorithm and one can show that xn will converge to mu, right? However, since we don't know mu, but instead we have access to h of xn plus mn plus 1, right? So what is this sum? So this sum is basically this quantity that is over here. Okay, so this is like, I'm sort of saying the same thing in several different ways. That is indeed true, but this is indeed what the how the analysis also proceeds, right? So I don't know the value of h of x. However, I know a value of h of x plus mn plus 1, right? And the fact that this has zero mean, okay, it is because of this reason that one can interpret this as adding noise to the value of h of x. Is this okay? So let me summarize. Ideally, I would have liked to evaluate the value of h at x, right? Let's say my current estimate is xn. This is ideally what I would have liked to evaluate, but unfortunately I cannot know the value since mu is not known. However, I can evaluate the value of h of xn plus mn plus 1. So this is referred to as noise on one hand because this is random and it has zero mean. Is this okay? Because even if it is not having zero mean, okay, one can think of this as a biased noise. Is that okay? All right. Okay, and an alternative explanation could be in the context of stochastic gradient descent. So as I said, in the context of gradient descent, the update rule usually looks like this. Okay, often it may not be possible to evaluate the know the value of the gradient of a function. However, it may be possible to evaluate or obtain a sample of the gradient of the function at xn. Right? So this sample is denoted by this expression in square bracket. Is this okay? And this is the expression that somehow captures all the noise that is there. So as I mentioned, this quantity over here is deterministic, right? Once you know xn, this function, okay, will spit out the a deterministic value. However, the noise in this algorithm at the nth step comes because of mn plus 1. Okay, and that's another reason, or that's another way to figure out why this is can be interpreted as the noise in the estimate. Okay, so I hope that sort of answers the question, right? And it will become even more clear as we look at an application of stochastic approximation. Okay, so this will form the bulk of this talk. Okay, I'll try and provide an application of stochastic approximation in the context of web crawling. Okay, and it will become clear to you, okay, why stochastic approximation is useful, and why we think of this mn plus 1 as noise, and so on and so forth. Okay. So let me pause here for a second or two before we advance with the discussion on web crawling. If you have any questions, please let me know. Are there any questions?
There aren't any in chat, sir.
Okay, so maybe we advance. All right. Okay, so now we will discuss this topic of web crawling. Okay. So I'll give some quick background about web crawling. So I would like to emphasize that this discussion is not about web crawling. So I won't give too much details about web crawling. However, I want to the focus will be on how stochastic approximation can be used to solve a specific problem in web crawling. Okay, but nevertheless, let me give you some quick background about what the area of web crawling is all about. Okay, so I'm sure everyone sort of appreciates and understands that the internet is humongous. Right. So what does the humongous mean over here? Well, humongous means that the internet has lots of interlinked data, right? So it has lot of data, and this data is interlinked. Okay, so by that I mean that if you go to a web page, okay, there are links. When you click on that link, okay, you are you are transferred to another web page that consists of more details that you may wish to look at, and so on and so forth, right? So in that sense, the internet has a lot of interlinked data, and importantly, both the data, right, and the links keep changing. Is that okay? So the internet is humongous in this sense. Nevertheless, when you as a user, okay, try to use a search engine to search some results with regards to some query that you may have, okay, you expect the search engine to provide search results almost instantaneously, right? So you don't expect the search engine to you don't give some what should I say, I mean, you don't say, okay, the internet is humongous, so I'm fine if the search engine takes some few hours and provides me the results. Okay, you don't say like that. You expect that whenever you put in the query, the search engine should give the answer almost immediately, right? So in order to do this, what a search engine does is that it doesn't search over the internet when you provide in a search query. Okay, instead, okay, it searches in a local database. Right. So more importantly, what is there in the local database? Well, a search engine maintains a local database where it has all the latest copies of vital or important web pages. Right. So a search engine decides, okay, here are the most important websites in the world. right? I will download a copy of these web pages on this local database. So whenever a user comes and puts in a query, it doesn't go and search at that time. It just looks in the local database, okay, fetches the answer and gives you back the answer. Okay, and this is the reason why a search engine is able to provide search results almost immediately. Okay, so that is the reason. Right. So, however, recall that this data and the links that are there on the internet, okay, they keep changing, right? So this database needs to be regularly updated. Okay, and the job or the task, okay, of updating is carried out by this, this thing which is called as a web crawler. Okay, so a web crawler is basically a software whose job is to keep regularly updating this local database that the search engine uses. Right. So what does the web crawler do? Well, the web crawler has several tasks. Okay, we will focus on two of its important tasks. Okay, so I would like to emphasize that these are not the only tasks of the web crawler. Okay, there are several tasks, but the two important tasks of the web crawler are as follows. Okay, it regularly visits these important web pages. So recall that the search engine has decided which are the important web pages. So the web crawler will regularly visit these different web pages, right? First, to see if it has changed or not, and second, to download the latest copy if the web page has changed, right? So I hope you agree that each web page will be stored on some server, and the server could physically be located in some very far off place, right? So whenever you put in your search query, okay, let's say in Google or Bing or DuckDuckGo or something like that, each of it will maintain its local database, right? So the local database will be updated by via this web crawler, which will visit these web pages on these far away servers. Okay, regularly it will visit them, check if the web page has changed. If it has changed, download the latest copy. Okay, so that's what this web crawler will do. Okay, so ideally one would expect that this web crawler should visit the web page as soon as it changes and download the latest copy, right? So this is ideally what the web crawler should do. However, I hope you agree that it is more realistic to believe that due to the sheer number of web pages and also due to finite bandwidth availability, right, one cannot access any web page infinitely often and also as and when one desires. Okay, in other words, there is some optimal frequency at which a page can be visited, right? So because of this bandwidth restrictions and so on, you cannot visit this page very frequently. However, there can be some optimal frequency at which you can visit this web page to check whether the page has changed or not, and if it has changed, download the latest copy, right? And in this paper that is was published in the year 2018 by Azhar and others, right, in that you can find the details that the optimal crawling frequency, so crawling frequency basically means the frequency at which you should crawl a particular web page, right? So this optimal crawling frequency depends on three parts. The first is the rate at which this page changes. This is the first thing. This is the rate at which the page changes. The second factor is this available bandwidth, right? And the third factor is how important this web page is, right? So of course, I hope you agree that some pages will be more important as compared to other pages. This can be judged based on how frequently some pages requested by users, right? So perhaps a page related to stock exchange, okay, would be requested by several of these users, right? So maybe that may be considered as an important web page. On the other hand, there may be some other pages which are not so frequently requested for. Okay, so that can be considered as some non-important web pages. So the bottom line of this discussion is that the optimal frequency at which a web page should be crawled, okay, typically depends on three factors. The first is the rate at which a web page changes, right? The available bandwidth and importance. Okay. Now, the focus of this talk will be on this part, the rate at which a page changes. Okay, so let's spend a couple of seconds on what this part means. Okay, so the first thing you have to agree, or I am sure you will accept, is that different pages change at different rates, right? So for example, if you look at a government web page, right? So a government web page maybe which is describing some bill or something like that. right? Describing some bill or describing some law. Okay, so this web page will change only if the law changes. Okay, and I hope you agree with me that these things take a very long amount of time, right? And consequently, these pages will change at an extremely slow rate. On the other hand, there could be pages, let's say, related to cricket or maybe related to the stock market and so on. Okay, so these pages, on the other hand, will change very fast. Right, so you can see that there are different pages and each web page changes at different rates. Okay, but the web crawler, okay, by default may not know at what rate this page changes. Right, and in order to decide how frequently this page needs to be crawled, it needs to know, or it needs to be able to estimate the rate at which this page changes. Right, and the main part of today's talk will be how to use stochastic approximation to estimate the rate at which a page changes. Is that okay? So even if you have not understood what I have discussed so far, okay, it may be a good point to rejoin the discussion. The discussion henceforth, okay, will focus on using the idea of stochastic approximation to estimate the rate at which a web page changes. Okay, so this part of the talk is based on a recent work which is jointly done with Konstantin Avrachenkov and Kishore Patil. Okay, so let me pause here for a second or two. If there are any questions with regards to this idea of web crawling and what we are going to do now, in particular, how we plan to use stochastic approximation, this may be a good point to ask. Are there any questions?
There aren't any chats, sir, but if anybody wants, they can unmute and ask.
All right. Okay. So maybe there aren't any questions. So maybe...
there is one question, sir. It's from Chetan.
Yes.
So out of curiosity, what is the order of magnitude of number of vital pages?
So maybe I'm not the right person to answer this question. Okay. So just 1 minute.
Just curious, that's all.
Yeah, I mean, I'm not the right person to answer this question. Okay, it may be best to ask someone who works in this, maybe in some search engine related company. Okay, so I don't know. Okay, all right.
Thank you.
Okay. So now we will. Yeah, go ahead.
Audible.
Yes.
Yeah, I had a doubt in the previous math in which the function was defined, the info till time n.
Can you repeat, like the function? Yes.
Yeah, so here, if why did this condition probability is independent of it, and why was it defined in the first place? I didn't
So
get
your
that.
question is, why is this relationship true? Is that the question?
Yeah, and if this thing is independent of that, why is it defined? Like, what's its use?
So you are saying that if anyway, this is independent of this, why did you use conditional expectation? Is that your question?
Yes, sir.
So I'm saying that in this case, so at this point, I'm making an observation, right? I'm not saying that, we have to take this conditional expectation or anything like that. All I'm saying that if you take this conditional expectation, it turns out to be 0. Okay, so this observation was with regards to a specific algorithm. In that specific algorithm, this conditional expectation did not depend on Fn, and consequently, this conditional expectation was equivalent to this unconditional expectation. Is that fine?
Okay. All right, sir. Thank you.
Okay, but the major point was that any a stochastic approximation algorithm is any iterative algorithm which in some sense satisfies these 3 conditions, that h is a deterministic function, right, and this mn plus 1, right? So stochastic approximation algorithm is any iterative algorithm of this, which is of this form, where alpha and we will view as a step size sequence, h is some deterministic function, and mn plus 1 we will think of as a noise, right? In particular, these are the random entities at time n, right? And this should satisfy this condition over here. Is this okay? So that's all I'm saying. Any stochastic approximation algorithm is basically an iterative algorithm which has these properties, right? Now, why did it turn out to be equal to this? That was because of that specific algorithm in context. However, in general, we don't require that this be independent of this. The only thing that we require is that this conditional expectation be 0. Is that okay? That's all we require. As long as we have such a thing, it will turn out to be the case that the iterative algorithm that we are interested in, that can be viewed as a stochastic approximation algorithm. All right. Okay, so now let us sort of discuss the setup. Okay, so recall what the problem is. Our goal is to use this idea of stochastic approximation to estimate the rate at which a web page changes. Okay, so what we will do is, we will sort of discuss this, setup, right? I'll sort of describe the algorithm, and maybe we can have a quick break after that. Okay, so after the break, we will sort of deal with the analysis of that algorithm. Okay, so here is the setup. Okay, so we have one web page. Okay, so we don't have to worry about multiple web pages. What we have to work with in this discussion is just with one page. Okay, so we have one page, and the goal is to figure out the rate at which this given web page changes. Okay, so we will presume that this given web page changes at times denoted by Sn, right? And we will presume that S0 is 0, that is at time 0 it changes. Thereafter it changes at S1, S2, and so on, right? And we will presume that the gap between Sn and Sn minus 1, right? So the gap between Sn and Sn minus 1, these are independent and identically distributed exponential random variables with unknown rate delta, right? With unknown rate delta, which means that the probability, so basically it means that Sn minus 1, this is an exponential random variable, right? So with rate delta, which basically means that if you look at the tail distribution of this random variable, that is the probability that the gap between Sn and Sn minus 1 exceeds u, this will equal e raised to minus delta u. Okay, so this delta over here is this delta over here. Okay, so when I say rate, I mean the inverse of the mean function of an exponential random variable. So I hope you know that if the tail distribution is this, then the mean of this will be the mean of this random variable will be 1 over delta. Is that okay? So the key thing to note here is that this page changes in this fashion, that is, it changes at time S0, it changes at time S1, it changes at time S2, and so on, right? And the gap between successive times at which the page changes, we are assuming that this gap, this sequence of gaps are IID exponential random variables with unknown rate delta. Okay, so when I say we would like to estimate the rate at which the page changes, the goal actually is to estimate this value of delta, right? And we will presume that we have a crawler, right? And this crawler accesses the page at times Tn, right? Where again T0 is 0, and the gap between these subsequent time instances, these are again IID exponential random variables. However, the difference between Tn and Sn is that we are implementing this crawler, right? So because we are implementing this crawler, okay, we would know the rate at which this will be visiting a particular page, right? So pictorially, this is the situation. So let's say we have this is the time axis, right? So these X crosses over here, this denote the times at which the page changes, right? So maybe it changed at time 0, maybe it changed at time S1, maybe it changed at time S2, maybe it changed at time S3, and so on. And we are assuming that the distance between them, okay, these are IID exponential random variables with some unknown rate delta, right? And at T0, we access this page. Then at time T1, we access this page again. Then at time T2, we access this page again. And at time T3, we access this page again, and so on. And we presume that the distance or the gap between these time instances at which we access this web page, okay, that is, these are again IID exponential random variables, but this time with some known rate P. Is this okay? Now observe what can happen between two time instances of access. The page could have changed multiple times, like for example here it changed twice, or it is possible that between two time accesses, okay, the page never changed, or it is possible that between two time accesses there was precisely one change. Is this okay? So all these different scenarios are possible, that maybe between two accesses there were multiple changes, no change, or maybe there was just one change, right? So what will the crawler get to know? So whenever it visits the page, let's say at time Tn, right? So the crawler will get to know the value of this indicator In, right? So what is this indicator? This tells us if the page has changed or not between time tn minus 1 and tn, right? So let's say it visited the page over here, right? Let's say it visited the page over here, and let's say it visits the page again at time t3. At this time, it will get to know the value of I3, right? Which will basically say whether the page changed or not, okay, with regards to the contents at time t2, right? So clearly this page changed at time s3, which is after t2. So if you access the page at time t3, you will indeed realize that the page has changed with regards to its earlier content, right? On the other hand, if you visited this page at t1 and if you visited this page again at t2, then the value of this indicator, that is in, okay, this will be 0, because the page did not change between t1 and tn, right? So the goal of this problem, okay, is to use these values of tn. So recall that tn, these time instances tn correspond to the times at which the crawler visits the web page. Okay, since we are designing the crawler, we would know that different times at which the crawler visits the page. So using access to this information, using access to these indicator variables, and also using the knowledge of p. So recall p is the rate at which we access this page, right? So using the values of tn, in, and p, the goal is to determine delta. Is that okay? So notice that we don't have the knowledge of Sn and we don't have the knowledge of delta. Instead, we have knowledge of tn, in, and p, and using just this information, the goal is to determine the value of delta. Is that okay? So let me pause here for a second or two. If there are any questions with regards to the problem setup and the goal of the problem, this may be a good point to ask. Let me know if there are any quick questions.
Yeah, I have a quick question. What if Tn and Sn are the same? Are you assuming that the
so we are assuming that these these Sns and Tns are independent processes, right? So with probability 1, they will never be the same. Is this okay?
Yeah,
right?
Thanks.
Okay. Is there any other question? Are there any other questions? So I hope the setup is clear, right? So there is a page, it changes at these times S0, S1, S2. We don't know when it changes. We visit the page at T0, T1, T2, and so on. And we would like to know the rate at which this page changes. So when I say rate, I mean this delta. Okay. And we can presume the knowledge of TNs, INs, P, and using just the knowledge of this, we would like to estimate the value of delta. Is that okay? So I will need maybe 5 more minutes to basically give the algorithm to solve it, and then we can take a short break, and then we can come back and analyze that algorithm, right? So before giving you the algorithm by making use of stochastic approximation, let me sort of tell you, if you sort of scan the literature and if you sort of try to find any paper concerning the topic of estimating the rates at which a page changes, okay, you will find a paper by Joe Garcia and so on, right? So I don't remember, I think it's a 2003 paper, right? So if you see like the well-cited paper, right, you will see a paper by Cho and Garcia from 2003, right? And it has like over like 450 citations, right? So if you sort of look at this paper and if you sort of see the method that is proposed in this paper, okay, the method that is proposed is that of the maximum likelihood estimator, right? So I'm sure most of you must have heard this term, but for those who are hearing it for the first time, the maximum likelihood estimator idea works as follows. It tries to identify the parameter value, which is delta in this case, that maximizes the probability of observing these INs, right? So we have observed these INs over here, right? So we would like to find that parameter value that maximizes the probability of making the observations, right? So whatever we have observed, what is the parameter value that maximizes the probability of these observations? Okay, so that's the idea of this maximum likelihood estimator, and this paper from 2003, which has a lot of citations, okay, that proposes this maximum likelihood estimator idea to estimate this delta value, right? And in the setup that we are assuming, okay, trying to use the maximum likelihood estimator idea is equivalent to solving this equation. Okay, so let me sort of go over this equation. Okay, so the equation on the left, okay, is of the following kind. It is a sum starting from k equals 1 to n, right? It has a fraction. In the numerator you have ik and tau k. So tau k is basically the distance or the gap between tk and tk minus 1. So recall that these are tks are the time at which the crawler visits the page. Okay, so we have knowledge of these tks, right? So accordingly we know the value of tau k. So you take this ik, multiply it with tau k, right, divided by the exponential of delta tau k and subtract it with 1. Is that okay? So you do this expression, right? Add this for different values of k until n, and on the right hand side you have another sum which is made up of 1 minus ik times tau k, right? So ik's are again these indicator random variables which tell us whether the page has changed or not, and tau k again is the gap, right? So in order to find delta, you are supposed to solve this complicated equation, right? So you are supposed to solve this complicated equation, and in order to determine an estimate of delta, right? So what are the immediate observations? The first thing is that, okay, let's say currently you have access to data until time n, right? And you then obtain a fresh estimate at time n plus 1, right? So as soon as you obtain this fresh estimate, you have to redo this calculation from scratch, right? This is because there is no easy way to make use of the solution estimate for n for the calculation at time n plus 1. So basically there is no easy way to reuse your calculations. Okay, so each time a new data value becomes accessible, okay, you have to solve this equation from scratch in order to obtain an estimate of delta. Okay, and consequently each time you try to solve this equation, okay, the computation time actually increases quite rapidly as the time index n increases. Notice that the time index n over here is in the super script of this summation. So as n increases, the number of terms you are adding keeps on increasing, and consequently when you try to solve this equation, okay, it is going to take more and more time. Okay, and furthermore, okay, you need to store all the values of these ik values. Okay, so you need I1, I2, all the values until IN, right? And only then you would be able to solve this equation. And similarly, you also need to store all these tk, tk minus 1 and so on, so that you have access to these tau k's, and only then you will be able to solve this equation, right? So in our paper, we proposed an alternative algorithm that makes use of stochastic approximation, and that is given in equation 2 over here. Right, so in equation 2 you have xn plus 1 is xn plus alpha n times in plus 1 xn plus p minus xn, right? So this is the update rule, and we are claiming that this update rule, if you run, right, you would be able to get better and better estimates of this quantity delta that we are interested in estimating. Is that okay? Now observe that this has a very simple update rule, right? You don't need previous values and so on. You just need the value of in plus 1. It makes use of your previous estimates and just improves upon them to obtain xn plus 1, right? And our main theorem in this work is that if you choose these step sizes of this form, then your iterates actually converge to delta almost sure. Is this okay? So maybe we can pause here for some time. Is 5 minutes good?
Yes.
Okay, so maybe we can pause for 5 minutes and rejoin at 12:30. I'll be available if some of you have.
What is small p here? Sorry to interrupt. What is small p here in your algorithm?
Yeah, so so recall that I had said that we access this web page at times t0, t1, t2, and so on, right? And I had presumed that tn minus 1, these are IID exponential with parameter p, right? So which means that the probability that tn minus 1 is greater than u, this is equal to e raised to minus pu. Is this okay? Or in other words, 1 over P is the expected value of this gap. Okay, the 1 over P is the expected value of this gap. Okay, so any gap, because these are IID, this is any gap.
So there is a question from Ajul who is asking, how is the distribution of P for visiting different pages assumed initially?
So that's a very good question, right? So in some sense, we are trying to figure out the rate at which we should visit different pages. So in some sense, we are trying to figure out what should be the ideal value of P, right? So the ideal value of P depends on delta, right? So it's a very good question. Like, to begin with, what should be the value of P? Right. So, so the quick answer is, you can, to begin with, you can assume some arbitrary values for this P, right? For example, if you have, let's say, 1 million pages, and you have certain bandwidth, you can take that bandwidth, divide it by 1 million, and basically that will determine the frequency with which you will access each of these 1 million pages. So what I'm saying is that initially you can access all the pages uniformly, right? And thereafter you sort of figure out which page changes at what rate. That is, you get hold of this delta, and thereafter you can accordingly change the value of P. I hope that answers your question, Arjun.
Yes.
Okay. So I hope it is fine if we restart at 12:30. Should we take maybe 5 more minutes, or whatever is convenient? Let me know.
12:30 should be fine, I think.
Okay, so maybe I'll just be back in 2 minutes. Okay. So Karim, I'm back. You can let me know when to restart. Okay.
Hello, sir. I have one question.
Yes, please.
So if you go back to your previous setup, that includes h function h and mn plus 1. So
you want me to go to the first page? Is that what you want me to do?
no, sir. That is okay. That there in equation 2, where you were initially.
Here, equation 2. Yes.
So what is here mn plus 1? It is
so we will look at that. We will look at that. Okay. So in the analysis, we will discuss these precise things. Okay.
So Professor Thope, there's a question.
Yes.
On the chat. Solution approach 1 using MLE seems to be independent of P, whereas the recursive algorithm 2 depends on P. Do you have any comments? That's the question.
Yeah, so that's a valid question, but in some sense, we are using some similar information. So notice that these TKs, they are exponential random variables with rate P, right? So this MLE solution makes use of these TKs, whereas we, instead of making use of these TKs, okay, we make use of the average distance between TK and TK minus 1 and TK. Right, so we are in some sense making use of similar knowledge. Is that okay?
Yeah, and quite possibly the way this equation is derived also uses the assumption that these TKs are distributed exponentially.
Yes, that is true. Okay. Okay, so may I continue, Karim?
Yes, it's 5 minutes now. We can continue.
All right. Okay. All right. So I think in the remaining time, our goal would be to sort of analyze these algorithms, right? So why is this algorithm good? Okay. So far, what you have to appreciate is that we were accessing this page, right? And our goal was to estimate the rate at which this page changes, right? And if you sort of went via this traditional approach based on this MLE estimation, right, you will end up requiring to solve such a complicated equation. Right, so I'm not sort of saying that this approach has any issues like the estimate that you will obtain, how good the quality would be, and so on. I'm not making any comments on that. The only comment that I'm making is how do we compute this equation, right? That's the comment on. The comment is not on the quality of the solution, right? How much time is required to compute the solution to this equation, right? And that keeps growing as n increases. Right. Furthermore, the issue is that we cannot, there is, at least I am not aware of, some efficient way of reusing our previous computations, right? Like, let's say we solve this equation for, let's say, n equals 100. Right now, if I obtained some new sample, right, I don't know how to solve this equation for 100 and n equals 101 by making use of the solution that we obtained for n equals 100. Right. So, of course, there are some, hand wavy tricks that one uses. Right. However, there are no, sort of well understood or, methods for which we can provide guarantees, okay, that this is indeed the right way to do, and so on and so forth, because you would have some errors, and, one will have to worry about whether the errors are accumulating, and so on and so forth. Right. So all those issues are there. Right. On the other hand, we are claiming that using the principles or the theory of stochastic approximation, one can come up with a neat algorithm. Right. So this doesn't need these past values, right? On one hand. On the other hand, implementing this algorithm is very, very efficient, right? So observe that the time required for each update, okay, is the same. It doesn't grow with n, right? Whatever time you require to do this multiplication and this addition, okay, that's the same amount of time you will require in each iteration. So the time required across iterations doesn't change. Right. And so that's the main benefit of using stochastic approximation. Right. So stochastic approximation provides you with some very cheap iterative algorithms. Is that okay? And so now our theorem says that even though you have such a algorithm, right, which is very different in form to the MLE approach, right, this algorithm, if you run, okay, almost surely this algorithm will converge to delta, okay, which is the quantity that we desire to estimate. Right. So now we will sort of, based on how much time is remaining, okay, I'll try and, analyze this algorithm. Okay. And two things will go in parallel. Okay. The focus would be to analyze this specific algorithm. Right. However, in the background, okay, we will also see how to, analyze generic stochastic approximation algorithms as well. Okay. Because the same ideas will sort of carry forward in the generic setup as well. Right. So let's make some basic assumptions or basic observations. Right. So the first observation is that.
Sir, there's a question in the chat, sir.
Yes, please go ahead.
Would it be correct to say that equation 2 is not based on MLE? That's the question.
So the question is, can we somehow rederive equation 2 using MLE? If that is the question, then no.
No, I guess I was just wondering if 2 is formulated independent of MLE considerations. Is that correct?
2 is formulated independently of MLE considerations.
Okay, thank
Is
you.
that okay? So I think your question is how, I presume you are asking, how does 2 compare with MLE?
But that's a follow-up. But the first question was that 2 is not based on MLE. That was which
it's not based on MLE. Yes, that's the short answer. And we will now see how can one come up with an algorithm of the form that is given in 2. Is that okay? So the whole theory of stochastic approximation enables you or empowers you to come up with iterative algorithms of the following kind. That is, one sort of benefit that you gain by studying stochastic approximation. The other benefit that you obtain is, it provides you with the tools to analyze such algorithms, right? So when I say analyze, you will be able to show that where does this algorithm converge to, how fast does it converge to, what is the impact of step size on the convergence, and so on and so forth. Is that okay? So those are the kind of questions that you can answer by making use of the theory of stochastic approximation. Okay, so let's do some quick observations. So to begin with, so recall that these I1, I2, I3 and so on, right? These are the indicators which tell us whether the page has changed or not with regards to the previous crawled instance, right? So these are IID because, the times at which the page changes and the times at which we access them, okay, they are also behaving in an IID fashion, right? So let I have the same distribution as any of these I1, I2 and so on, right? So this is some generic random variable which has the same distribution as this, right? So then if you sort of use your knowledge of probability theory, okay, with some effort, you will be able to show that the expected value of this random variable is indeed given by delta over delta plus p, right? So of course, delta is unknown. So consequently, the expected value of I is not known, right? So now what we will do is we will define this function capital H, right? So we are very carefully and smartly designing this capital H function. Okay, so how do we design this? We design it by trial and error, right? So we sort of play around with few choices of this H function, right? And we sort of see if it works or not, right? So it has to work empirically, meaning in our experiments it has to work. It should be useful to estimate delta, and secondly, okay, it should also be according to the theory of stochastic approximation, so that one can prove convergence guarantees and so on and so forth, right? So we sort of cook up this function h of x. So if you ask me how did we cook up this function, well, the answer is that we did a lot of trial and error, and we spent few days figuring out, oh, will this h work, will this h work, and so on, and eventually we came up with such a capital H, right? And so this is how we define it, right? So this capital H function is I times x plus p minus x, right? So I would like to draw your attention to the algorithm that we actually implement. Okay, so the algorithm that we actually implement is precisely this. That is, it is in plus 1 xn plus p minus xn, right? So this precise quantity is what is your capital H function, right? So let little h be defined as the expected value of this capital H function, where the expectation is taken with respect to this random variable I. So notice that in this definition of the capital H function, right, the only thing that is random is this quantity I. Everything else is either the input or something that is a deterministic constant, right? So the only thing that is random is I. So if you take the expectation of this function with respect to I, right, so then you can see that this little h function satisfies the following property, right? So expected value of I is just delta over delta plus p. So I've copied this x plus p as it is, and the x over here comes down as it is. Okay, so by some massaging, you can see that this function has the following form, right? So that is delta minus x over delta plus p, the whole thing multiplied by p. Right. So the key thing to observe is that this function h over here has the following form, right? It is of the form b minus a times x, right? Where b, okay, where b is delta p over delta plus p. Okay, so just observe this quantity. I have just written b as delta p. So okay, so I've just chosen this thing and this thing. Okay, so this is my b, and similarly I'm looking at the expression that multiplies x. So I hope you agree that a is basically p over delta plus p. Is this okay? Right? So if you sort of recall our algorithm that we used to estimate this delta, right? So now I can rewrite this update rule in the following form, right? So I can write it in the following form, right, where this expression I rewrite it as h of xn, and since I am artificially introducing this h of xn over here, whatever is over here I subtract h of xn from that, okay, and that I refer to as mn plus 1, right? And by some simple calculations, you can show that mn plus 1 has the formula that is given over here, right? So the bottom line here is that this is an algorithm that is useful for analyzing or estimating delta, and for the purpose of analysis I can write it in this form, where this little h, okay, this little h has the form that is given over here, okay, which is indeed of the form b minus ax, and mn plus 1 has this form over here, right? And the way we have constructed everything, okay, you can easily see that if we define this calligraphic fn again in this form, then the conditional expectation of mn plus 1, okay, as in that warm-up exercise, turns out to be 0, right? So in this sense, this is the driving function that we would have ideally liked. However, again, notice that the definition of h depends on delta. So this is something that is unknown, right? However, while we cannot estimate the value of h of x, we can obtain an estimate of the noisy value of h of x, right? And the noise over here comes from mn plus 1, and one saw that its conditional expectation with regards to the history that is there at time n, this is again 0. Is this okay? So these are the facts that we can make in the context of the algorithm that we have at hand. So let me pause here for a second or two. If there are any quick questions with regards to this algorithm and the value of h and the value of mn and so on, this may be a good time to ask. Are there any quick questions? All right, so I don't see any questions, so maybe I advance. Is this okay? All right. Okay, so now we sort of deal with the serious, more technical stuff. If you somehow come up with an algorithm, right, how do we analyze it, right? So how do we analyze it? In meaning, one of the basic questions that one can ask is, where would an algorithm, let's say of this kind, converge to, right? Where would an algorithm of this kind converge to? So that is the kind of questions that we would like to ask. Okay, so one of the popular ways of answering this question, okay, is via what is called as the ODE method. Okay, ODE over here stands for ordinary differential equation. Okay, ODE here stands for ordinary differential equation. Okay, so the popular approach for discussing the convergence of a stochastic approximation algorithm is the ODE method, right? So how does the ODE method work? So first, let's look at this particular ODE, right? So for the time being, we will forget, the stochastic approximation algorithm. Let's say we have some function h, and let's say we look at the following ordinary differential equation, right? So the way to interpret this ordinary differential equation is that you can think of x of t as the position, right? So this is the position, and you can think of this as its velocity. Okay, so the ODE basically describes the velocity of a particle as a function of its position, right? So wherever the particle is, the ODE tells you this should be its velocity, right? And based on that velocity, the position of the particle will change, and as soon as the position of the particle changes, the ODE will specify what should it be, its new velocity, and so on and so forth. Okay, so this equation basically relates what the velocity of the particle should be to the position of the particle, right? So when I say a solution of an ODE, right, whenever I say we have a solution, I mean a function of time. Okay, so this is a function of time, right? So this specifies, or this is a curve, this you can interpret as the position of a particle at time t, right? Okay, at time t, which satisfies this relation, right? So if you have, let's say, a particle which at time t is at x of t, so for every t you have some position, right? If that curve satisfies this relationship over here, right, then we will say that it's a solution. Right now I would like to just draw your attention, like when we have an equation, let's say of the form x square equals 2, right, the solution to this is plus minus root 2. So this is just one value, right? However, when we have a differential equation, the solution to it is a trajectory. In other words, it's a function, okay, to which you give as input time and it specifies the position, right? So it's a function which is a solution to this relationship that we have over here. Now there is a specific solution or a specific problem in the context of ODE, which is referred to as the initial value problem, right? So in that we require a solution which require in some sense a trajectory which satisfies this equation. In addition, at some specified time t naught, it has to pass through some specified point x naught, right? So whenever I say we have a solution to the ODE, henceforth we will presume that there is some initial point x naught, right, and there is some initial time t naught. So I would like to find a curve x of t for different values of t, such that at time t naught this curve or this particle is at x naught, and thereafter it satisfies this relationship that is specified in 3, right? So such a curve will be referred to as a solution to this which satisfies this condition over here. Is this okay? Now, this is something from the ODE theory. It is known that if this function h that you have, right, if it's Lipschitz continuous, then one can show that any initial value problem, okay, has a unique solution. Okay, so that is one thing. Now, if you have someone who has maybe read a bit about this numerical approximation techniques for finding solutions to the ODE, you must have heard something called as the Euler approximation. Right. So what is the Euler approximation? Well, pictorially, it is what is shown over here. Right. So let's say you start from x naught at time t naught and you have this red trajectory. Right. So this red trajectory is basically the solution to this ODE over here. Right. The solution to this ODE, right, which at time t naught is at x naught. Right. Now, the Euler approximation is basically an approximation to this trajectory that we have over here, right? So often, you must have seen that, solving a differential equation is very hard. However, computing an approximate solution is not that hard. The reason that we can compute an approximate solution is that, the derivative at any given time, let's say Tn, right, we can sort of write it as the value of the trajectory at time tn plus 1 minus the value of the trajectory at time tn divided by, okay, so divided by tn plus 1 minus tn, right? So the derivative of the trajectory at time tn, okay, if I choose this tn and tn plus 1 very close to each other, I hope you agree that x of tn plus 1 minus x of tn divided by tn plus 1 minus tn, okay, this will approximately equal, okay, the derivative of x at time tn, right? And because we know that x dot of tn must equal h of x of tn, okay, from this it follows that x of tn plus 1 x of tn plus 1 minus x of tn by tn plus 1 minus tn, okay, this should approximately equal h of x of tn, right? So if you sort of denote the value of x of tn by xn, okay, then the above relation can loosely, and let's say you denote this tn plus 1 minus tn as some alpha n, then this above relation that you have, that can be written as xn plus 1 minus xn over alpha n. This is approximately h of xn, right? So if you sort of use this approximation, so this will be your x0, use this approximation to compute x1, okay, use the same approximation to compute x2, x3, and so on, right? And if you sort of linearly interpolate these different values, okay, you will end up with a trajectory of the following kind, okay, and this one can see, or one can check that this would be an approximation to this red trajectory. Is that okay? So what is the Euler method to approximately compute the solution to a given ODE? Well, the Euler method to compute the approximation is basically given by this equation over here, which is based on this idea that we have formulated over here. Okay, so if you want to compute an approximate solution to the ODE, what you do is, let's say you start from x0, right, and you define alpha 0 to be, let's say, t1 minus t0, alpha 1 to be t2 minus t1, and so on, right? And from x0 you use this update rule. X1 is x0 plus alpha 0 h of x0, and then x2 is x1 plus alpha 1 h of x1, and so on, right? So in this way you can compute this quantity, this quantity, this quantity, and so on. And if you linearly interpolate them, the trajectory that you will end up with will indeed be an approximation to this. So now one can ask, why are we discussing this Euler approximation and so on? So if you notice this, you will see that, this is exactly how my stochastic approximation algorithm looks like, right? So the difference between this and a generic stochastic approximation algorithm is that in addition to h of xn, I have this mn plus 1, right? So a stochastic approximation algorithm can be viewed as a noisy Euler approximation to the solutions of the ODE x dot of t equals h of x of t. Okay, so now let me summarize what happened. Let's say you are given a stochastic approximation algorithm that looks like this, right? So you have been given a stochastic approximation algorithm that looks like this. If you are aware of the Euler method for finding approximate solutions, you will notice that this exactly looks like the Euler method for finding an approximate solution, except that there is a additional noise term over here. Because of this, we can view any stochastic approximation algorithm as a noisy Euler approximation to the solutions of this ODE. So whatever h you have in the update rule for your stochastic approximation algorithm, that same h, okay, you sort of use in defining this limiting ODE, right? In defining this ODE, and this ODE will be referred to as the limiting ODE corresponding to this stochastic approximation algorithm, right? So let me summarize what we have done. Let's say you have a stochastic approximation algorithm which has the form that is given over here. Whatever is the h over here, you use that h to construct an ODE. This ODE is deterministic, right? This ODE that we have over here is deterministic. Why is this deterministic? Because this h that we have over here, okay, this is deterministic. Because h is deterministic, this ODE is deterministic. Its solution trajectories will be deterministic. And what we are saying is that this stochastic approximation update rule that we have, that can be viewed as a noisy Euler approximation to the solutions of the ODE. So what this means is that if you can understand this deterministic ODE, right, in particular its behavior, right, like if you start a solution of this limiting ODE from some x naught, where would its trajectories converge to, right? So that will give us a good indication of where a stochastic approximation algorithm would possibly converge to, right? So that's what the ODE method is all about. It basically makes use of the properties of the limiting ODE and the properties of the noise sequence, and sort of uses the behavior of the ODE to say something about the asymptotic behavior of the stochastic approximation algorithm itself. Okay, so here is a theorem from the book called Stochastic Approximation, a Dynamical Systems Perspective by Professor V.S. Borkar, right? So if you look at this textbook, in particular, if you look at chapter 2 of this book, okay, you will see this theorem. Okay, so the theorem goes as follows. So let us say you have a stochastic approximation algorithm of the following kind. Okay, then the theorem says that almost surely, right, the iterates of this algorithm converge to an attractor of this limiting ODE, right, under the following conditions. Okay, so these are the different conditions. I'll come to that. Okay, but the first thing I would like to elaborate is that what do I mean by an attractor, right? So let's say you are given this limiting ODE, then an attractor in the context of a ODE is the set to which the solutions of the ODE tend to evolve towards. right? So often this attractor could be an isolated point, it could be a set, and so on and so forth, right? Like for example, it is possible that an attractor is a circle, so that whenever you start the solution of an ODE, maybe the solutions sort of converge to this circle that is there, or maybe if you start the solution from outside, maybe the solutions will sort of spiral towards this blue thing, right? So observe that for whatever initial point you choose, okay, the solutions either go towards this blue circle from inside or from outside. So in that sense, one can see that this circle can be viewed as an attractor, right? So often the attractor could also be a point, right? And this theorem basically says that if you have a limiting ODE, right, if you have a limiting ODE, then the iterates, that is xn, converges to the attractor of this limiting ODE under the following conditions. Okay, so let me quickly go over these conditions, right? So the conditions are that this function h, this is allowed to be a function from RD to RD, and we require that this function be Lipschitz continuous. There are some conditions on the step sizes. The conditions are that the step sizes should be, the sum should be infinity. However, if you take the squares of these step sizes, this should be finite. Okay, we require that, this noise sequence Mn be a martingale difference sequence, right? So one of you had asked me at the beginning, right, can this Mn or this noise sequence, can they be more generic than this IID? Well, the answer to that is yes, they can be more generic than the IID as well. Okay, the generic condition is that, we require that it be a martingale difference sequence. Okay, that is, so whenever I say martingale difference sequence, I basically mean that your noise sequence Mn plus 1 should satisfy a condition of the following form. Right, and there are some additional technical conditions. I mean, because of lack of time, we will not go over it, right? And under all these conditions, okay, so there are a bunch of conditions, right? So if you sort of ensure that all these conditions hold, okay, the loose idea at the end of the day is that this stochastic approximation algorithm will indeed asymptotically behave like the trajectories of this deterministic ODE. That's the key thing. This is a deterministic ODE, whereas this is a stochastic approximation algorithm, right? What we are saying is that, under some conditions, this basically starts tracking the solution trajectories of this deterministic ODE. So consequently, whatever is the behavior of the solution trajectories, we can basically use that to say something about the behavior of this stochastic approximation algorithm, right? So there were a bunch of conditions. Okay, one can verify all these conditions. Okay, so I don't want to spend time on that. Okay, we can verify all those conditions, and eventually one can show that for the algorithm that I had shown for this web crawling problem, okay, that algorithm indeed converges to delta almost surely. Okay. So just one last point, right? So one can ask, why did I choose this algorithm, okay, of this form? So if you remember the algorithm that I had chosen, right, for estimating this delta, okay, it had the form as shown, as I'm showing right now, right? So why did I choose this form that is over here? Well, the answer to that is that if you look at the limiting ODE, that turns out to be something of the following kind, right? Notice that this is a deterministic ODE, and the good thing about this deterministic ODE is that delta turns out to be a delta is a globally asymptotically stable equilibrium for this ODE, right? So why did I choose such a form for this update rule? Well, the answer is that its limiting ODE is nice. In particular, the quantity that we wanted to estimate, okay, that quantity turns out to be the globally asymptotically stable equilibrium of this ODE, which means that whatever solution of this ODE you look at, it will always converge to delta. Is that okay? So that's the reason this ODE is nice, and consequently this algorithm, okay, does the job that it was, the purpose for which it was designed. Okay, so with this, maybe I'll stop. If you have any questions, this may be a good point to ask. Thank you. So Karim, I'm done. Let me know if you have any questions. I'm happy to take as many questions
Yeah,
as
if anybody has
possible.
any quick question, please ask. It's almost time.
Yeah, I have a question.
Yes.
Will the same arguments go through if we assume that the visitation times of the of that web page are sub-exponentially distributed rather than exponentially?
So see that. So I mean, the answer to that is one will have to verify it, right? So we haven't checked this, right? However, this conditions under which convergence is guaranteed, okay, this is quite general. Is that okay? So unless there are some serious issues with the way you are trying to execute your algorithm, one would expect that the limiting ODE will behave nicely, and as long as the limiting ODE behaves nicely, one would expect that your algorithm will also track the limiting ODE. Is that okay? Right? But the point is that the times at which we access this web page is something that we can control. True. Is that okay? Right? Yeah, so one can, the first question I would like to ask is there some specific reason why you are wanting to choose something that is sub-exponential or something like that? Right? So although we have not analyzed it, at this point, I don't see any reason why it shouldn't work. Of course, the analysis may become quite complicated. Okay, so the exponential distribution gives a lot of elegance, right, and so on and so forth. So that sort of helps in simplifying the analysis. However, for other distributions also, okay, it may be possible, but the calculations may become quite tedious. Is this okay?
But it seemed as if you used the exponential property only to arrive at the form of the the stochastic approximation algorithm, and after that, it's just the ODE method which takes over.
Precisely, right? See, the point, I mean, you are correct. See, every ODE, right? So, see, every ODE, x dot of t equals h of x of t, right? Every ODE is trying to give us a new stochastic approximation algorithm, right? Whatever h you choose, right? So this, can be thought of as helping us come up with a stochastic approximation algorithm. So you are right that the way we come up with an algorithm will, mean that the limiting ODEs will turn out to be different. Is that okay? But whatever these limiting ODEs are, as long as they are well behaved, your algorithm can also be shown to be well behaved in the same sense. Is that okay?
Thanks.
Yeah.
There is another question in chat box. Is asking just for the clarity whether the attractor may not be the solution of the ODE.
Can you repeat? Sorry.
Asking for the clarity, the attractor may not be the solution of the ODE.
See, the attractor is either a set or like in the simplest case, it could just be a point, right? So, so let's say, for example, this is an attractor. So let's maybe I'll explain it a bit carefully. So let's say we have an ODE of the following kind, and in this case, what happens is that P is of the form delta P over delta plus P, and A turns out to be P over delta plus P, right? And consequently, B over A turns out to be delta, right? So my claim is that delta is a globally asymptotically stable attractor for this ODE. So what that means is that if you let's say define a trajectory in the following form, that x of t is equal to delta for all t, right? For all t, that is, you start at delta, right, and you remain at delta for all t. So the claim is that because delta, okay, is special, one can show that this trajectory. So notice that this is a trajectory in the sense that for all t, x of t is at delta itself. That is, the particle stays at delta forever, right? So that actually satisfies this relation over here. The reason being that whenever you substitute or replace x of t with delta, so b minus a times delta, right? Because of the way we have defined b and a, and because delta satisfies this relation that it is b over a, you will see that it turns out that this right hand side is 0, right? So because the right hand side is 0, right, if you start at delta, the velocity is 0, so you continue to remain at delta. right? So and consequently this is an equilibrium point, and in order to show that it's an attractor, one additionally needs to show that whatever be the initial point, if you sort of run the solution of this ODE, you will actually converge to delta. Okay, so I hope that answers your question.
There are other questions also.
Yeah.
Like from Subhendu Vasini is asking, P is chosen by the user. Does the value of P have any effect on the convergence rate?
Yes, it does have an effect on the convergence rate, right? So, however, so there are some restrictions on. So the answer is yes, it does affect the rate at which the algorithm converges, right? However, there are some restrictions on how we can choose P, right? Because as I mentioned, we are given some bandwidth, and within that bandwidth itself, the search engine has to update its local database. So the whole discussion that we had in this class pertain to one web page. However, in the context of a search engine, it has to update several web pages. So, there is some constraint on how large P can be, and the convergence rate does depend on it. So I would like to emphasize two things. See, when you talk of convergence rates, there are two parts. One is the constants in the convergence rates, and one is the order at which the error decays. The order at which the error decays, that doesn't depend on P. However, the constants in the convergence rate do depend on P. Right, the order at which the error decreases, that usually depends on the step size, right? Like for example, if you choose alpha n to be of the form, let's say 1 over n to the power sigma, where sigma is let's say some constant between half and 1, half not included, right? So in that case, one can show that the expected value of xn minus delta, okay, this is like order of 1 over n raised to sigma over 2. So my point is that there are some constants in this order that may depend on P. Okay, however, this part, okay, this only depends on the choice of the step size. Okay, however, when we choose alpha n to be, let's say, of the form 1 over n, okay, then the convergence rate may also depend on the choice of P. That is, the decay rate itself may depend on the choice of P. Right. So I hope that answers your question. Are there any more questions?
There isn't any, but somebody is asking about notes, whether that will be provided. Apart from
I mean, I am fine. In case there is some medium in which you can share, we can discuss it later. Okay.
Okay. Yeah. Okay. So there is no more questions. So yeah, if somebody has quick, otherwise time. I think there is no more question in the chat and nobody is asking. So I think we can wind up soon.
Thank you. Thanks a lot. Okay.
Thank you.
Okay. Bye.
Before we leave this, so you can just stop sharing your done. So I just like to announce for the next session. You can join us at 2 o'clock. There will be preliminary talk by Professor John he is from ETH Zurich, and the title is Data Enabled Predictive Control. So please, you guys do join us at 2 o'clock. So that's it for this session. So we can leave now. So I'm ending this session. Thank you, everyone.
Thanks, Karim, for coordinating this.